Okay. All right, so today's edition of Basement Physics, we are going to, I'm going to scoot the camera up as I do it. We're going to start to talk about electric field. Now, last year we talked about electric field. It is an abstract concept. So this is where, girls, we're going from, from something that should, I hope, electric force, make some sense. And even though we can't see those charges, hopefully you can kind of visualize what that might look like. When we talk about electric field, it's starting to become more abstract, and we're going to use this a lot for the next couple weeks. So absolutely let me know if you have questions as we're getting into this work. So electricity is one of the field forces, right? All of the field forces have what we call a field. And so the broadest way to define field is the area in which the force acts. So just conceptually, that's what we're saying. So if we have two charges, where's my marker? I go off camera while I get a marker, sorry. If I have two charges, let's say that I have two positive charges. So I have a positive charge here, and I have another positive charge right here. There is going to be, as we know, a force between them. Since they're both positive charges, this is going to be a repulsive force. So there's going to be a pushing away from both of them. The question is, like, how does this charge talk to, it's not really doing that, of course, this charge? How does the force travel across space? And so when field forces were studied, and this is still something that's, it becomes part of modern physics, really. But when field forces were studied, they were looking for a way to quantify that. To quantify how does the force from, let's say, the charge on the left reach the charge on the right, and vice versa. And so that was called the field. So in gravity, which is actually the very first the very first field force that was studied, we also have a gravitational field. We didn't talk about it a lot when we studied it last semester, but the gravitational field, as it turns out, is all that fabric of space stuff that we would talk about last year. So it's actual bends in space-time. That's the gravitational field. And if I take a mass out, like let's say I have the sun disappear, we talked about how that would create a ripple in that fabric of space-time, and that would be a sudden change in the field, or a disappearance of the gravitational force. So electricity, it looks a little bit different, but it's kind of that same concept. So electric forces act across distances, and that area in which it's acting is called the electric field. Now, when we define the electric field, we define it as the area, it tells us how a positive charge would behave if placed near another charge, okay? So if we're gonna have what we call the charge producing the field. So on the board over here, the charge that I have drawn in black will be the charge producing the field. And then you'll see this term test charge used. And so I will draw the test charge in blue. So if my test charge is here, and I have this charge in black producing a field, again, these are two positive charges, right? So the test charge will be repelled. It would be pushed away. If I move the test charge up here, it would be pushed up towards my basement ceiling. If I put it on the left here, it would be pushed to the left. And so as we can see, wherever I put that blue test charge near the charge producing the field, it's going to be pushed away. So when we draw field lines are just a way that we visualize this field, this area in which the force can act. The field lines are going to be drawn always, always, always as coming out from positive charges. So, and again, in this case, the black charge on the board is the charge whose field I want to study. And so if I want to visualize that field, they're going to be vector lines, right, drawn coming out of that charge. So it's showing me that if I put a positive charge anywhere in this field, a repulsive force would act and make that positive charge move away. Now, let's say my test charge, so test charges are just defined as being positive. Again, it's a little bit abstract, just when we make the equations, we say let it be positive. But If I put a negative charge into the field, then what it would do is move in the opposite direction, right? So the field is drawn as showing me what would happen to a positive charge. So we have all these lines pushed out. And I just know then, well, let's say I put an electron into the field. Well, then it's going to do the opposite. It's going to be sucked right in. If we drew field lines for a negative charge, so if I come on over here, so I'm going to have, again, in black, the charge that is producing the field. And let me try losing this light. Wait a minute. Oh, look, that glare went away. Is that so much better? Okay. So in black is the charge that is producing the field, and I'm going to put a test charge in the area. So again, test charge defined as being positive. If this positive charge were right here, it would be pulled into, right, the negative charge, because these are opposite charges and they're going to attract. If I move the positive test charge over here, it would still be pulled into, and you get the idea. Anywhere that it is at in the vicinity of the negative charge, it would be pulled in. And so if I'm going to visualize that with field lines, they're going to be vector arrows drawn moving into the negative charge. So field lines, when we draw them, are always, 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 because they're defined by what would happen to a positive test charge. They're always pointing out from positive charges and in to negative charges. So it's an important conceptual thing to know. Out from positive charge, in to negative charge. If you have multiple charge arrangements, you'll see them start to curve a little bit. You also will see, it depends on what's being visualized, whether it's like a textbook or something online or you writing on paper. People will either draw more field lines, that's most typical, draw more field lines to indicate a stronger field, and then they would draw fewer lines if the field were weaker. So your textbook does that, that's what most things do. Or sometimes color is used to visualize that. So the field lines become lighter as you move further away from the charge, for instance. The electric field strength is dependent on two things conceptually. One is the charge. So if this is a really big charge here, the electric field is going to be stronger. If it's a smaller charge, it's going to be weaker. The other thing that impacts the electric field is how far away you are from the field. So from the charge, I'm sorry. So the further away you are from a charge, the weaker the field will be. So there are two equations that we're going to work with the problems for this first homework set from chapter 22. There are two equations we're going to work with electric field. And one is always true. So you can do some pretty complex things with field, and it can have a lot of calculus, and we'll dabble with it towards the end of the week. But this equation is always true. The electric field tells us how the electric force acts on a test charge. So mathematically, we represent it this way. I'm not really deriving, again, just because of time and space. But we can say electric field is electric force divided by Q, where Q is the charge of the test charge, so the thing that's placed into the field. This is always true. So whether I have some of these crazy charge distributions that require calculus or just a really simple arrangement, this equation is always true. The second equation that we will be using is the equation for the electric field from a test charge. So it is equal to K, or 1 over 4 pi epsilon naught, remember those are the same thing, times Q divided by R squared. And sometimes you see this Q, actually, let me write it as this. Sometimes you see this Q as a capital Q. It doesn't really matter. So this is true only for point charges. Again, different video will work a little bit more with that, but what I mean by that is this is true. You can use this equation when you are finding the electric field from one charge or from maybe two charges. Oh, you heard my dehumidifier's on. It just went off. I sound loud. Or 3 charges or 4 charges. This equation would not work if you had a billion charges. You would have to do integration, really. So this equation works when you have a small discrete number of charges. K is that constant. Q is the charge producing the field. So like in this case, it would be the charge of the black positive charge. And R would be our distance away from the charge. And so we would measure this, or if you look at the top equation, field is measured in newtons per meter because it's force divided by charge. You end up with the same units, of course, down here, force per meter. I am going to remind you in my assignments for the week that last year when we studied electric field, we did an online example called electric field hockey, if you remember, where you were placing charges and arranging them. And I would encourage you to take a look at that again. I think it's a really good way to visualize what is a little bit abstract. So remember, when you do electric field hockey, you're placing charges, which would be like my example here, the black charges that are producing the field. And then you take a test charge, which is your puck, and you put it into the field and you press play. And you see how that field produces a force, which makes the test charge move. So I would encourage you to take a look at that again before you dive into some of the problems.